Well, I think this example is a good one. This is a famous old example of the principles of Gestalt psychology, which are the principles by which we organize information. And when you first look at this picture, it's very hard to figure out what it is. In fact, it just looks like a bunch of light and dark splotches, and you may look at it for a while and just see light and dark splotches. And that actually is the information that your eye is getting from this picture, and your brain has to figure out what to do with it. Now I can show you what you should do with it, because we've here drawn some lines on top to show you that there's a dog there. It's a Dalmatian dog, and the Dalmatian dog has these light and dark spots on it. And if we go back to the original picture now.
Unbelievable.
Isn't that unbelievable?
Yes.
That's fantastic.
Now that you've seen what it really is, now you can hold that image together and you can see how to organize it. This is a picture of a cylinder casting a shadow on a checkerboard.
Right.
And you'll see there's two checks. There's a dark check labeled A and a light check labeled B. And it's quite obvious when you look at it that one of them is dark and one of them is light. But the fact is that the ink on the page is exactly the same. If you were to be a light meter and you were to measure the gray level of the ink for A and the ink for B, it's exactly the same ink. So it seems like a failure, like the visual system is not managing to do this very simple thing of tell you what color the ink is on the page. But that's because the visual system's job is not to tell you about ink on a page, it's to tell you about what's out there in the world.
The thing about this image that's so striking is that although this process can be written down and described the way Ted describes it, you would have thought you could unpack it. You could have said, okay, well, now that I know that A and B actually have the same color on the page, I should be able to see them as though they are the same. But you can't. It's absolutely automatic. It's built into a low level of your visual system to tell you about the checkerboard and not about the shadow.
Both of you have had experience with computer vision, and you might just sort of discuss how, difficult it is to even come close to the way the normal visual system. We can recognize each other's faces with enormous facility. Computer vision has enormous difficulty doing that. Perhaps you elaborate on that.
Yeah, let me give you one specific example of that. So a computer vision system for face recognition, the cutting edge computer vision system would require a facial image that was at least 100 by 150 pixels in its resolution. The human visual system can work with images as degraded as this. These are maybe about 12 by 14 pixel images.
Right.
And we can achieve recognition rates on these images that are superior to a computer vision system working with images that have 100 times more resolution than this. So just as Ted said, it doesn't seem like we can get to this level of performance just by making incremental improvements. We need to have a qualitatively different
understand the logic of the visual system.
Absolutely.
Yeah. Well, one of the things that's key for the visual system's success in doing this is what Ted was talking about earlier, which is its ability to throw away the information that's incidental. So to throw away where the light happens to come from, how the face happens to be posed, where the shadows happen to fall.
How do we know how that happens?
Well, we know from the cylinder on the checkerboard what some of the principles are. We do not know exactly how that happens in detail. If we did, we would have written a computer program to do it, and the computers would be as good as we were. And a classic example is a cube. This is not Necker's cube. This is just a cube. And if you have a wireframe cube, you don't normally have any difficulty interpreting it as a cube. But if you have a wireframe cube of which you have made an image on a piece of paper, as, for example, in the case of the images here, there is a bistability to the image. You can actually see this image in two different ways. So if you look at the cube on this side, what most of you will do is see this as a cube with this face near and this face, the one that's behind, far. The cube on this side, which has information encoded in a slightly different way in the image, will represent itself with this face near and the other one far. Now if you look at the cube in the middle, by a simple inspection, either by passive inspection or maybe by an effort of will, you can actually see that cube in either form. Either
Yeah.
You can see it flipped.
Absolutely.
You
Yeah.
can't see it both
Yeah.
ways.
Yeah.
You have to see it one
Yeah.
way or the other,
Yeah.
right?
I
And
just saw it just flip, yeah.
Yeah.
now, one of the striking things about this Necker cube, in addition to its flipping, is that the one thing you don't see is actually, in many ways, the simplest thing you could see. And so here's a Necker cube image again, but
Wow.
this Necker cube image, as you can see here as I hold it up, is in fact a flat object, which isn't a cube at all. It's in many ways the simplest possible interpretation of the image. It's just a series of lines on a piece of paper. But this interpretation is the one you never see. And the question of why the visual system constructs this three-dimensional representation out of the information is one of the questions that we'll have to answer if we're going to answer questions about, for example, how complex objects are represented and recognized.